In this lesson, you are going to understand the concept of feature engineering. By the end of this lesson, you will be able to demonstrate feature engineering and its significance using Python, practice different feature selection techniques. Go ahead and understand feature selection in detail. Why do you need feature selection and what are its benefits? Feature selection is used to select those features that contribute most to the prediction variable that you are interested in. Benefits of feature selection. It reduces overfitting by making data less redundant, which creates less opportunity to make decisions based on noise. It also reduces training time by eliminating the misleading data. This ultimately improves the modeling accuracy. It also improves the accuracy by collecting fewer data points. This reduces the algorithm complexity and enables you to train the algorithm faster. Let's understand feature selection through a problem statement. Given a multidimensional data set, extract information based on interrelations among variables. Look at the given table. Is there any interrelation among the variables? If there are interrelations among the variables, then how will you find them? So, to draw the right conclusion from a statistical analysis and to find out the interrelations among the variables, it is very important to understand the relationship between variables. Statistical relationships between variables are dependent on notions of regression and correlation. The two techniques used for feature selection are regression and factor analysis. Regression. First, look at how regression can help you in feature selection. Regression indicates the relationship among variables and quantifies the relationship using a set of equations. Regression analysis attempts to determine the best fit between two or more variables. The independent variable in a regression analysis is a continuous variable and thus allows you to determine how one or more independent variables predict the values of the dependent variable. What happens when you have multicollinear data? Interdependence between two or more explanatory variables may lead to an unreliable model. How will you make such a model reliable? The solution is to perform factor analysis to extract the underlying causes leading to this behavior. Let's now look at factor analysis in detail. Factor analysis is used to reduce a large number of variables into fewer numbers of factors. This technique puts the maximum common variance into a common score by extracting it from all variables. You can look at the given graph and understand that the common factors of the observations explain the variable interdependence. In factor analysis, multiple observed variables are all associated with a latent variable, so they have similar patterns of responses. In every factor analysis, there are the same number of factors as there are variables. Each factor contains a certain amount of the overall variance in the observed variables, and they are always listed in order of how much variation they explain. Eigenvalue is a measure of the variance that a factor explains for the observed variables. Any factor with an eigenvalue less than 1 explains less variance than a single observed value. In the example given, you can understand the relationship between the observable variables and the observable outcome. Here, observable variables are minutes browsed, clicks, page views, and add to carts, whereas the observable outcome is sales. So all the observable variables ultimately are associated with a latent variable that in this example is sales. There may be a few underlying causes that can affect the output apart from the observed ones. In this example, apart from page views, clicks, add to cart, minutes browsed, and sessions, there are a few other underlying causes such as selection, marketing, spend, and pricing, which also can affect the outcome, that is, sales. Note, identifying underlying causes is part of factor analysis, and it helps in accurate prediction. Factor analysis process. Factor analysis focuses on analyzing the underlying causes that can affect the output apart from the observed ones. There are two commonly used algorithms to perform factor analysis, specifically PCA and LDA. Although PCA and LDA are both factor analysis algorithms, they have significant differences. PCA extracts hidden factors from the dataset and defines your data using less number of components, explaining the variance in your data, while LDA reduces dimensions by searching for a linear combination of variables that best separates two classes. PCA reduces computational complexity, while LDA reduces the degree of overfitting. PCA determines whether a new data point is part of the group of data points from your training set, while LDA determines how to classify a new observation out of a group of classes. Principal Component Analysis, PCA. Let's look more closely at principal component analysis. Here is a scatter plot of data points plotted over X and Y axes, such that each dot shows one particular observation. Applying PCA over the data points will yield a new set of axes, say PC1 and PC2, such that they cover the maximum information. They are orthogonal to each other as well. This means that the obtained principal components PC1 and PC2 will have zero correlation and are ranked according to the variance of data. The data around PC2 is projected along PC1 to ensure that no variance is lost. In order to extract the maximum variance from the variables, PCA seeks a linear combination of variables. Some directions are better represented. Direction along maximum variance contains maximum information. You need to compute eigenvectors that are the principal components of a dataset and collect them in a projection matrix. Each of those eigenvectors is associated with an eigenvalue, which can be interpreted as the length or magnitude of the corresponding eigenvector. The reduction of the dataset via PCA onto a smaller dimensional subspace by dropping the less informative eigenpairs is reasonable when some eigenvalues have a significantly larger magnitude than others. Project the remaining eigenvector on x-axis and then try to project it along the y-axis by drawing a red line through it. Try to collate all the values on the same line by normalizing the values to the axis and direction of the red line. The new set of axes found are orthogonal to each other. Let's try to understand how the projection points are orthogonal. PCA finds the best line depending on two different criteria. One, first, the variation of values should be maximal along this line. Notice the spread of the red dots change while the line rotates. Second, if we reconstruct the original two characteristic positions of a blue dot from the new position of a red dot, the reconstruction error should be minimum.